In this video, I'd like to tell you about the principal components analysis algorithm. And by the end of this video, you know how to implement PCA for yourself and use it to reduce the dimension of your data. Before applying PCA, there's a data pre-processing step which you should always take. Given a training set of m unlabeled examples, it's important to always perform mean normalization, and then depending on your data, maybe perform feature scaling as well. So this is very similar to the mean normalization and feature scaling process that we had for supervised learning. In fact, it's actually exactly the same procedure, except that we're doing it now to our unlabeled data x1 through xm. So for mean normalization, we first compute the mean of each feature, and then we replace each feature x with x minus its mean. And so this makes each feature now have exactly 0 mean. And then second, if the different features have very different scales. So for example, if x1 is the size of a house and x2 is the number of bedrooms, to use our earlier example, we then also scale each feature to have a comparable range of values. And so similar to what we had with supervised learning, we would take I subscript j, that's the j feature, and so we would subtract off the mean, now that's what we have on top, and then divide by Sj. Here Sj is some measure of the range of values of feature j, so it could be the max minus min value, or more commonly it is the standard deviation of feature j. Having done this sort of data pre-processing, here's what the PCA algorithm does. We saw from the previous video that what PCA does is it tries to find a lower dimensional subspace onto which to project the data so as to minimize these squared projection errors. The sum of the square projection errors is the square of the length of those blue line segments. And so what we wanted to do specifically is find a vector u1 which specifies that direction, or in the 2D case we wanted to find two vectors u1 and u2 to define this surface onto which to project our data. So just as a quick reminder of what reducing the dimension of the data means, for this example on the left, we were given examples xi, which are in R2, and what we like to do is find a set of numbers zi in R with which to represent our data, right? So that's what reduction from 2D to 1D means. And so specifically, by projecting the data onto this red line there, we need only one number to specify the position of a point on the line. So I'm going to call that number z, or z1. Z here, this is a row number, so that's like a one-dimensional vector. So z1 just refers to the first component of this, one-by-one matrix, right? This one-dimensional vector. And so we need only one number to specify the position of a point. So if this example here was my example x1, then maybe that gets mapped here, and if this example was x2, maybe that example gets mapped here, and so this point here would be z1, and this point here would be z2, and similarly, we would have those other points for these maybe x3, x4, x5 get mapped to z1, z2, z3. So what PCA has to do is we need to come up with a way to compute two things. One is to compute these vectors, u1, and in this case u1 and u2, and the other is how do we compute these numbers z. So on the example on the left, we're reducing the data from 2D to 1D. In the example on the right, we would be reducing data from 3-dimensional, so xi is in R3, to zi, which is now 2-dimensional. So these z vectors would now be 2-dimensional, so it would be z1, z2 like so, and so we need to give a way to compute these new representations, the z1 and z2 of the data as well. So how do we compute all of these quantities? It turns out that a mathematical derivation, or sort of a mathematical proof for what is the right value for u1, u2, z1, z2, and so on, that mathematical proof is very complicated and beyond the scope of the course. But once you've done all that math derivation, it turns out that the procedure to actually find the value of u1 that you want is not that hard, even though so that the mathematical proof that this value is the correct value is somewhat more involved and more than I want to get into. But let me just describe the specific procedure that you have to implement in order to compute all of these things, the vectors u1, u2, and these vectors z. Here's the procedure. Let's say we want to reduce the data from n-dimensional to k-dimensional. What we're going to do is first compute something called the covariance matrix. And the covariance matrix is commonly denoted by this Greek alphabet, which is the capital Greek alphabet sigma. It's a bit unfortunate that the Greek alphabet sigma looks exactly like the summation symbol. So this is the Greek alphabet sigma. It's used to denote a matrix, and this here is a summation symbol. So hopefully in these slides there won't be ambiguity about which is sigma, the matrix, the covariance matrix, and which is a summation symbol. And hopefully it'll be clear from context, when I'm using each one. Having computed this matrix sigma, and let's say we were to store it in an octave variable called sigma, what we need to do is then compute something called the eigenvectors of the matrix sigma. And in octave, the way you do that is you use this command, usv equals svd of sigma. SVD, by the way, stands for singular value decomposition. This is much more advanced singular value decomposition. This is much more advanced linear algebra than you actually need to know, but it turns out that when sigma is a covariance matrix, there are a few ways to compute these eigenvectors, and if you're an expert in linear algebra and if you've heard of eigenvectors before, you may know that there's another octave function called eig, which can also be used to compute the same thing. And it turns out that the SVD function and the eig function will give you the same eigenvectors, only SVD is a little bit more numerically stable. So I tend to use SVD, although I have a few friends that use the eig function to do this as well. But when you apply this to a covariance matrix sigma, they'll give you the same thing. That's because the covariance matrix always satisfies a mathematical property called a symmetric positive semi-definite. You really don't need to know what that means, but the SVD and the eig functions are different functions, but when they're applied to a covariance matrix, which can be proved to always satisfy this sort of a mathematical property, they'll always give you the same thing. Okay, that was probably much more linear algebra than you needed to know. In case none of that made sense, don't worry about it. All you need to know is that this is a command you should implement in Octave. And if you're implementing this in a different language than Octave or MATLAB, what you should do is find a numerical linear algebra library that can compute the SVD or singular value decomposition. And there are many such libraries, for probably all the major programming languages, and you should be able to use that to find a routine to compute the matrices U, S, and V given of the covariance matrix sigma. So just to fill in some more details, this covariance matrix sigma will be an n by n matrix. And one way to see that is if you look at the definition, this is an n by 1 vector, and this here, xi transpose, is 1 by n, and so the product of these two things is going to be an n by n matrix. Right, so it's 1 by n, is xi transpose 1 by 1 is 1 by n, so that's a n by n matrix, and when you add up a bunch of these, you still have an n by n matrix. And what the SVD outputs is 3 matrices, U, S, and V. And the thing we really need out of the SVD is the U matrix. So the U matrix will be also an n by n matrix. And if we look at the columns of the U matrix, it turns out that the columns of the U matrix will be exactly those vectors, U1, U2, and so on, that we want. So U will be an n by n matrix. And if we want to reduce the data from n dimensions down to k dimensions, then what we need to do is just take the first k vectors. And that will give us U1 up to UK, which are the k directions onto which we want to project the data. So to describe the rest of the procedure from this SVD numerical linear algebra routine, we get this matrix U, and I'm going to call its columns U1 through UN. So just to wrap up the description of the rest of the procedure, From the SVD numerical linear algebra routine, we get these matrices U, S, and D. And so here's the matrix U, and we're going to use the first k columns of this matrix to get U1 through UK. Now, the other thing we need to do is we need to come up with a way to take my original data set, X, which is in Rn, and find a lower dimensional representation, Z, which is in Rk for this data. So the way we're going to do that is I'm going to take the first k columns of the U matrix. So I'm going to construct this matrix. I'm going to stack up U1, U2, and so on up to UK in columns. It's really basically taking this part of the matrix, right? The first k columns of this matrix, and so this is going to be an n by k matrix. I'm going to give this matrix a name. I'm going to call this matrix U subscript reduce. It's sort of a reduced version of the U matrix, maybe. I'm going to use it to reduce the dimension of my data. And the way I'm going to compute Z is going to let Z be equal to this U reduced matrix transpose times X. Or alternatively, to write out what this transpose means, when I take the transpose of this U reduced matrix, what I'm going to end up with is these vectors now in rows. I have U1 transpose down to UK transpose, and then take that times X, and that's how I get my vector Z. Just to make sure that these dimensions make sense, this matrix here is going to be k by n, and X here is going to be n by 1, and so their product here will be k by 1, and so Z is a k-dimensional vector, which is exactly what we wanted. And of course, these x's here, right, can be examples in our training set, can be examples in our cross-validation set, can be examples in our test set. And for example, if I want to take training example I can write this as xi, and that's what will give me zi over there. So to summarize, here's the PCA algorithm on one slide. After mean normalization, it says ensure every feature has zero mean, and optionally feature scaling, which you really should do feature scaling if your features take on very different ranges of values. Because after this pre-processing, we compute the covariance matrix sigma, like so. And by the way, if your data is given as a matrix like this, if you have your data given in rows like this, if you have a matrix capital X, which is your entire training set written in rows, right, x1 transpose down to xm transpose, this covariance matrix sigma actually has a nice vectorized implementation, so that you can implement in Octave. You can implement sigma equals 1 over m times x, which is this matrix up here, transpose times x, and this simple expression, that's a vectorized implementation for how to compute the matrix sigma. I'm not going to prove that this is a correct vectorization, but if you want, you can either numerically test this out yourself by trying out an Octave and making sure that both this and this implementations give the same answers, or you can try to prove it yourself mathematically. Either way, but this is a correct vectorized implementation for how to compute sigma. Next, we apply the SVD routine to get U, S, and D, and then we grab the first k columns of the U matrix to get U reduce, and finally this defines how we go from a feature vector X to this reduced dimension representation Z. And similar to k-means, if you're applying PCA, the way you'd apply this is with vectors X in Rn, right? So this is not done with the x0 equals 1 convention. So that was the PCA algorithm. One thing I didn't do was give a mathematical proof that this procedure actually gives the projection of the data onto the k-dimensional subspace, onto a k-dimensional surface that actually minimizes the square projection error. The mathematical proof of that is beyond the scope of this course, but fortunately the PCA algorithm can be implemented in not too many lines of Octave code, and if you implement this in Octave or MATLAB, you actually get a very effective dimensionality reduction algorithm. So that was the PCA algorithm. One thing I didn't do was give a mathematical proof that the U1, U2, and so on, and the Z's and so on that you get out of this procedure is really the choices that will minimize the squared projection error, right? Remember we said what PCA tries to do is it tries to find a surface or a line onto which to project the data so as to minimize that squared projection error. So I didn't prove that this actually achieves that, and the mathematical proof of that is beyond the scope of this course. But fortunately, the PCA algorithm can be implemented in not too many lines of Octave code, and if you just implement this, this is actually what will work, or this will work well. And if you implement this algorithm, you get a very effective dimensionality reduction algorithm that does do the right thing of minimizing this squared projection error.